Hello everybody and welcome to today's video on calculus and vectors. Today we'll be going over chapter 1.4, which revolves around limits and continuity. Today we're going to take a look at the properties of limits as well as what limits have to do with discontinuities. So let's get started. As we learned in chapter 1.3, the limit of a function can be found using its graph. However, it is also possible to find the limit of a function algebraically. Limits have distinctive properties that can be applied when evaluating a certain limit. Those properties are the following. So the first property that we see is the limit over here of a certain value c, and we're saying that it will equal to c. So if you had the limit of 5 as x approaches 5, the answer would be 5. If you have a straight line, no matter what point you choose, the value at that point will always equal to 5. Similarly, over here we're seeing that the limit of a certain value is equals to a as x approaches a, means that if we had a diagonal line, if we took any point along that line, so if it was 1, you'd see the answer as 1. If you had the point 20, you would see the answer as 20. The next one is a little bit more complicated, but all it's saying is that if you took the limit of two functions together, so for example, your first function is x squared and your second function is 5. So you're taking the limit of x squared plus 5. All that is the limit of x squared and the limit of 5. This will allow you to easily break apart difficult functions into their most basic properties, because if you get x squared and 5, we know what 5 equals to. It's here. X squared can be applied to this function here. It could also be applied to other properties we see down below, so let's continue with that. The fourth point is the limit of c times the function. C again is just a constant, so all that equals to is the limit of the function times the constant. So if you're taking the limit of 0.5x, it's the same as 0.5 times the limit of f of x. Point 6 is very similar to point 3, or sorry, point 5 is very similar to point 3, and that is if you take the limit of two functions that were multiplied together, so if you multiplied x and 5, so the limit of 5x, that would be the same as multiplying the limit of 5 and the limit of x. Now for point 6, it's the division part. So again, it's very similar. If you divided it x squared by x, it's the same as finding the limit of x squared and dividing by the limit of x. If you could simplify it, of course, do that. However, if you can't, this is very useful. The next one is the limit of f of x to the power of n. So if you had f of x is equals to x and n is equals to 2, you could either evaluate f of x, so lim of x squared, or you could find the limit of x and then square that. Similarly, if you had the root of something, so like the fourth root of f of x, you could do the same procedure. You would find the limit of x and then take the fourth root. These concepts are all fairly simple, but you should definitely practice them in order for you to understand them. And for that reason, I've actually decided to have these two little examples here. Notice that last class, we actually learned that if you find the limit of a continuous function, that limit would equal to the substitution for x into f of x. So here, if our function was x to the power 4 minus 16 divided by x plus 2, we could try to substitute negative 2 into the equation, But immediately we're faced with a big problem, because if we substitute -2, we actually get -2 plus 2, which is 0, and we know we can't divide by 0. So you could easily say that, hey, that doesn't make any sense. We can't divide by 0, so this has no answers. However, as you will see, we can actually get around this problem, which is the beauty of limits. So let me show you how. Okay, so I've written down our question, and now let's get around to solving it. Immediately, we need to think back to the properties of the limits I just told you about. So first, what you could do is try to apply them, or what I personally like to do is actually try and factor the function that we were given. So if we try to factor this function, we actually get x squared minus 4 and x squared plus 4. Because remember, this here is the difference of squares, and thus we could apply this factoring to it. Again, the denominator doesn't change, so we get x plus 2 on the bottom. You could always, I think you should always write down the limits, because that way you know what you're actually doing instead of writing down random formulas or random expressions, and thus that's what I will be doing throughout the video. So now, as you can see here, we still have the difference of squares in the numerator, so let's continue with that. So again, the limit, and now x squared minus 4 is the same as x minus 2 times x plus 2 times x squared plus 4 divided by x plus 2. So now we actually see we have a common factor in the numerator as a denominator, so we can actually cancel them out. Okay, so from here we can actually simplify this, and so we get the limit as x approaches -2 of x minus 2 times x squared plus 4. We can now either substitute -2 for everything here and solve it that way. However, since I do want us to practice using the different properties of limits, we will actually go more in depth with this. So the first property that we know is, of course, f of x times g of x, and that would give us the limit of x as x approaches -2 of x minus 2 times the limit, so you could do like a little times, the limit as x approaches -2 of x to the power of 2 plus 4. Now, these are also properties that we learned about. The first property, or actually it's the same for both of them, is the addition, right? The only difference is this negative, but remember, a negative is just the addition of the opposite sign, and so we could just do that. So our right hand side, or sorry, our left hand side will be the limit as x approaches -2 of x minus the limit as x approaches -2 of 2. Again, this all will be multiplied by this side, which would be the limit as x approaches -2 of x squared plus the limit as x approaches -2 of 4. 3 out of 4 of these limits we actually know because of the fundamental properties. So we know over here we could just substitute x and we get -2. Here it would always be the constant, and so we get -2. The limit of x squared is the same as the limit as x approaches -2 of x to the power of 2. And then again, since we know that this is a constant, we just add 4. So simplifying this side, we get -4. Limit of x as x approaches -2 as -2 squared plus 4. Plus 4 all on this side. And so we get -4 times 4 plus 4, which is 8, which is equals to -32. And thus our answer is -32. Again, if we were just to plug those values in here, we would get -2 minus 2, so -4 times -2 squared is 4 plus 4, which is equals to -32. So doing either way is fine. However, if you choose to do it this way, you could potentially run into an error where you don't notice that there is a discontinuity within those terms, which is why it's always like much safer to do it the long way as we did here. But again, since we know that these are will not be restricted any further, in any case, like if x was any value, we could not get a value that's not real, and thus you could just safely plug it in. Again, just follow what your teacher says. I don't want you to lose any marks. So why exactly did we do this? Why did we have to find the limit of this function? Well, as I said before, if we look at the function that we were given, we actually found out that we can't technically have a limit because f of x is not defined at -2. However, we just proved that the limit as x approaches -2 will equal to -32. So if we had to draw this graph, for example, we could have had something like this. We had like a graph here, and then a hole, and then we continued. This value does not exist, right? Because it's a hole. We can't possibly say there's something there when there's clearly nothing. But what we found is that if you find the limit, so as the graph continues this way and this way, they do approach the common value. And that value in our case is -32. And so we just proved, or we just found what that hole should equal to. So at -2, the graph would have had the value of -32 if there wasn't a hole, if we didn't have to factor out these two values. So now, hopefully, you understand why limits are extremely useful when it comes to graphs, but you also just got introduced to the concept of discontinuities. For example, this one here is a removable discontinuity, since we just proved we can remove the hole by finding the appropriate value that would plug it in. Again, there's a lot more of these, which is what I would like to show you now. So now let's talk about limits and discontinuities. In past courses, we actually learned about functions that have certain features that restrict its domain or have certain gaps within their graphs. Those features were holes and vertical asymptotes. It's very important that you realize it was only vertical asymptotes, because horizontal asymptotes didn't actually change the domain. The only thing that it changed, it restricted our range. So these features were actually telling us that the graph is not continuous. It is discontinuous because there are certain gaps that are not filled. Now, in calculus, we actually need to understand that there are a little bit more graphs that have these types of discontinuities within them. And so I want to show you those different types. The first thing you have to learn is what a piecewise function is. That sounds very complicated because you don't know what it is, but essentially it's just when you put one function with another side by side. So for example, I have 3 here. We just took a line, and then we put another line, and then we put another line. This together is a function, because remember, the definition of a function was that for every x value, there's only one appropriate y value. So in our case, there's a y value here, no y value here, and all the y values continue on this line now. Once we reach to this point, we see that there's no y value here, but as soon as we move a little bit to the right, the y values continue, and so this is indeed a function. The same goes for all of the ones here. This one, they just took half a parabola, or like 3/4, and then slapped on a line to it. Again, just combining 2 or more functions together to create a single function. The problem, or the difficulty with these types of functions is when it comes to analyzing them. For example, here we have half a parabola, then we go down to this part, and then we go up. We can talk about the different segments of this function by just restraining each of the certain functions that we actually used. So if we knew the equation for this function, which we could figure out because we have a vertex and we have 2 key points, we would find that equation and then restrict it so it's less than or equal to -1. Then we find the equation for this line and we'd say, oh, it has to be greater than -1, but it has to be smaller or equal to 3. And then we do that same procedure for the last piece. So the analysis is not that complicated, but it could get a little bit tedious because you'll have to find the different equations for each of the different functions that were involved and then correctly restrain their domains to create a singular function. What's important for this particular class is the fact that 1 and 2 are both discontinuous, while 3 is not. You could probably tell that 2 is discontinuous because you were going from this side, then you went all the way down, and it's a completely different graph, and then you went back up, and now it's again a parabola. However, that's not really a proper way to think about it. The reason why they're discontinuous I'll actually discuss on the next slide. So the discontinuities that we need to know all have special names, and the ones that you should be familiar with for this course I have actually listed out. So the first one that we need to talk about is removable discontinuities. So that was the example that I gave you with when you had to find the limit. So these discontinuities actually have a hole. You could find these types of discontinuities occurring whenever a rational function has the same factor in the numerator as in the denominator. If those two things are the same, you could cancel them out, and that will allow you to find the limit. When you're finding the limit of those values, so at those holes, you will actually see that if you were to substitute the value in, you'd get the form of f of x is equals to 0 divided by 0, which doesn't make any sense, right? You're taking nothing and dividing it by nothing, and then you're saying, oh, you know, we could actually get a value from this. But essentially what we're actually dealing with is the indeterminate form of f of x. Because at this stage, we really don't know anything, and thus it actually allows us to know something. It's really fun if you think about it, but all you need to know for now, or all you need to understand, is if you see 0 divided by 0 being obtained in your equation, that means it can probably find the limit, and that discontinuity that you have will be a hole. The next discontinuity that you need to know is infinite discontinuities, and that is essentially your vertical asymptotes. For these discontinuities, we actually cannot find the limit because as soon as we start creeping onto the vertical asymptote, the function could either both go to positive or negative infinity, so both branches go to the same side of infinity, but they don't really reach a value because we're not treating negative or positive infinity as a specific value. It's just something in mathematics that we use to explain really large numbers that continue increasing more and more and more. And thus, technically finding the limit of it would not do us any good. Also, we get a problem when if one side goes to negative infinity and the other side goes to positive infinity. In this case, the right-hand side limits and the left-hand side limits will not equal at any point, and thus again we will have no limit. The next kind of discontinuity you need to know is the jump discontinuity. And that is the one that I actually showed you in these two examples. A jump discontinuity is just simply what occurs when working with piecewise functions. Again, it doesn't always happen, but it happens most of the time due to the nature of just combining two functions and then restricting their domains. Because as I said, a function has to have only one corresponding y value for every x value, and so when you do that, you might have a discrepancy between the first function and the second function. So the way that you know if a jump discontinuity has occurred is that the left-hand side limit does not equal to the right-hand side limit. So, for example, again, if we go back here, as we were approaching the limit from the left-hand side, it seems to have equal to 1. However, if we approach it from the right, the values are actually approaching to -2. And since 1 is clearly not -2, we can safely say that there is a discontinuity at that point, and thus, since the values are changing from 1 to -2, it should be a jump. Again, if you are too lazy or it's just a multiple choice question, you could simply just see, are the values jumping? Did this value just magically move up to a certain space or move down? So from here, we jumped down 2 spaces. Here, there are no jumps. Everything can be drawn with one line. If it was a whole, we're not necessarily jumping from any value because they're still following the same path. Same thing with infinite discontinuities. You're not jumping from one side of the asymptote to another because you're gonna go all the way to infinity, and thus you can't really say you jumped over the asymptotes because you can never actually touch it. So the next two are actually not part of the textbook, but I want you to know them nonetheless because they're pretty important for your understanding. The first one is restricted domain, and it is exactly what it sounds like. It's when you actually restrict the domain of a function in order for it to make sense. So for example, the square root of x we know has to be defined for when x is greater or equal to 0, because if we took the square root of -1, that is not a real number, that's an imaginary number, and thus that doesn't really fit with the definition of mathematics that we're working with. So these types of functions actually look continuous from where the function's actually defined. So if we look at the side where x is greater or equal to 0, we see a beautiful curve that is continuous. However, at the point 0, we actually cannot find a limit, because remember, in order for a limit to exist, the right-hand side must equal to the left-hand side, and since the only values that exist for this function are on the right, we cannot find the limit on the left-hand side, and thus 0 doesn't have a limit. The last type of discontinuity is probably the most vague one, and that's an oscillating discontinuity. Essentially this one, again, is not going to be taught to you in this course. You're probably not going to hear about it until university, but it occurs for certain functions when the y values oscillate infinitely often within a finite interval. Again, that sounds super complicated, but just all that means is that your y values, they jump from up, down, up, down, up, down in a very small interval, right? So instead of jumping up and down like in the sinusoidal function where you go to 1 and then 360 degrees or 2 radians later, you're back up, you actually do that super quickly within a really small interval. So here is an example, sine over 1x. If I bring over the graph of sine of 1x, you immediately can see what I mean. And so here it is. Here is the graph. As you can see over here, it's kind of making sense, but then as we get very close, you could see the decimals itself is freaking out, because what's actually happening is that the values of y become super close together, but they also are jumping from 1 to -1 within like a fraction of a thousandth of x, right? And so over here, we can actually say that although it might not seem like a discontinuity because you are jumping up and down, you can make a straight line through it, but it'll be super, super difficult for you to actually do anything. And thus you can't really get the value. Also, if you plug in 0, if you were trying to find the limit as x approaches 0, you'd have to evaluate sine of 1 over 0, which we know is not defined. And so, again, although the values seem to be jumping from -1 to 1, so they go up and down from 0 extremely quickly, we still know that the value at 0 does not exist. And so this is what we call an oscillating discontinuity. Again, if that sounded too complicated, do not worry about. It's just something fun for you to know about. So hopefully you understood everything I talked about today. Again, it was probably a lot of information because believe me, it really is. But it is really important for you to understand all of these different concepts before we go into the core of calculus in grade 12, and thus please learn this material. So if you want to do some extra homework today, here is the questions. It's 4, 6, 9, and 11, 12, 13. I actually will check on the page in just a second because it seems like I forgot to change it. So yeah, the page number was actually 44. I quickly fixed it. All of these questions will be either about analyzing the graphs and finding the limits of them, or it'll be about actually finding the limit of a function if you want to do it that way. An important part, I think, for 12 is to actually do this example here, because what you'll actually need to do is multiply the top and bottom by the numerator. So again, if you just multiply everything by square root of 1 minus x minus 1, the overall function will not change its value because you're multiplying it by technically 1. But if you multiply the top, or you square the top essentially, you'll get rid of the square root and you'll be able to solve the limit, because otherwise if you plug 0 back in, you again just get the value of 0 over 0, which we know now is a whole. And so I really encourage you to try that question out yourself. If you have any troubles with doing that, I'd recommend just leaving a comment down below and I'll quickly make a video on how to do those types of questions. But yeah, either way, thank you so much guys for listening to today's video. I hope you learned a lot of things today, and I cannot wait to see you next time. Bye bye!